Our next speaker, Manuel Asorey from Universidad de Zaragoza, Asymptotic Freedom and High Derivative Gauge Theories, please.
Thank you very much. Good morning to everybody. Buenos días, Spanish people who are quite populated this afternoon here in Spain. First, I want to start thanking the organizers of this meeting for conveying so many people working in different areas of theoretical physics and different countries. And I remember my first participation on this series of workshops in 1998 in Valdivia. It was the tercer encuentro de física de altas energías. And one of the things which impressed me at that time was the high interaction with high school students, and in particular, the list of subjects were discussed with them. If you remember, top quark physics, which was a hot topic at the moment, was one of the subjects. Another one was dark matter in the pre-Lambda CDM framework. And also very remarkable study of neural networks. It's quite impressive at that moment. But now my contribution at this time will focus on, as was said by the moderator, in high derivative gauge theories. This is based in a recent work done in collaboration with Fernando Forceto, Leslie Rajal, and Ilya Shapiro. The recent interest on this kind of theories involving higher derivatives comes from the fact that they can provide a robust approach to quantization of quantum gravity in a full field theoretical framework. On the other hand, from the phenomenological todo side viewpoint, there are successful models of inflation, like the Stirlingshire model, which involve theories of gravity with higher derivatives. And from the part side, the standard model, which is now, as was said previously, an effective field theory, there are completion of this theory in the ultraviolet, and there are a lot of them, but among them, one of the possible candidates is the high derivative theories. However,
I'm not sure, sorry, we only see the first slide.
No, oh, sorry. Maybe there is a problem.
Now we see the second one. Okay.
Okay, thank you. So in this standard model, there are many fields. You have scalar fields, the Higgs field, you have quarks and leptons, spin-on half fields, and you have vector fields. The UV completion of the first two species of fields gives rise to finite theories. But gauge fields and interaction of gauge fields with the other fields cannot avoid the fact that you have one loop UV divergences. So from this viewpoint, gauge fields are very special. And the same problem happens with gravity. So you have one loops, you cannot escape even if you introduce higher derivatives. The reason why these theories were disregarded in the past was because they involve ghosts, and these ghosts are dangerous, so they might induce violations of causality and unitarity. However, as we will see later, in recent times, there are many ways of avoiding this difficulty. So let me just concentrate on the case of higher derivative gauge fields. So for that, I consider a model, which is this one. You have a standard Yang-Mills theory, not quarks, not matter fields. And you add to that theory higher derivative terms, which is quadratic in curvatures, and they have in the middle of the two curvatures some covariant Laplacian. In this case, the particular choice is the Hodge covariant Laplacian operator, which is given by this expression here, or in more formal language using differential form, this one. And the particular property of this kind of high derivative theories is that they do preserve all classical field theory, solutions of the equation of motion. In particular, instantons are also solutions of the equation of motions of this theory in the Euclidean. So in each topological sector, these solutions are the minima of the minimize the action. So, but how do one-loop divergences behave here? Here is the computation for the down in alpha gates for the two-point function. You see it has the normal structure with transverse propagator. But there are two coefficients in front. One is depending on the gauge group you consider, Casimir of this gauge group. The other one is a coefficient which only depends on the number of derivatives you supplement to this gauge series. And this number, Cn, has this specific value for any value of a higher derivative n larger than 2 or equal. And it has two different values for n equal 1 and n equals 0. Of course, n equals 0 is the standard Young-Mills, and you have this contribution well known, but which is depending on the alpha gauge. In the other case, the divergent contribution does not depend on alpha gauge. This is a huge advantage of that case. And the second remark here is that the value for n equal 1 does not coincide with the plug-in in the generic formula for general n equal to 1. These two numbers do not match. Okay, but this, we understand why this happens. It's well known. So this requires renormalization. The renormalization we do perform is just not the minimal one. We add some finite renormalization just to match in the infrared with the standard QCD behavior of the Young-Mills theory. And with this renormalization, the theory is finite. It has a running of the coupling constant, which is given by this expression, where Cn is the number we have seen before, which for large n is here. Sorry, say something? Okay, so the important remark is that if you require that the theory is asymptotically free in the infrared, sorry, in the ultraviolet for high energies, then only very few theories satisfy this property. Just n equal to 0, ordinary gauge theories, n equal to 1, n equal to 2, n equal to 3, n equal to 4, and that's it. N equal to 5, you have here the current number, and is positive. And from that on, all of them are positive. So the requirement of asymptotic freedom restrict very much the theories of high derivatives you have to consider. So the finite part of the propagator now is again transverse because gauge invariant is preserved. And but the form factor, which is involved in this propagator, has two pieces. One which depends on the scale of the theory, which is given by this parameter lambda. We consider much larger than the, let's say, 100 TeV, and infrared part, which involves the QCD scale. So both of them have coefficients in front. The QCD1 has a constant coefficient, which does not depend on the number of derivatives. The other one does depend on this value n. So in a picture, what you have are two scales. One, which is the ultraviolet scale, where the beta function is given by this formula, which involves this famous coefficient Cn, which is negative for n larger or equal than 1 and lower than 5. And in the intermediate regime, where the momentum is between this high energy scale and the scale of QCD, you have the standard QCD running coupling constant. So in a plot, you have these two regimes. Here is the scale of lambda, this parameter of the theory. And below that, you have a unique behavior. It's like QCD1, is asymptotic freedom, standard asymptotic freedom regime. And for higher energies than this scale, the theory splits depending on the number of derivatives you have. You have only these 5 theories here, and all of them have different slopes, so different beta functions. So the largest deviation from the standard behavior is the n equal to 2 theory. This is very special theory. Yes, so this asymptotic freedom requirement is very stringent condition and selects very few theories. And if you enhance the higher renormalization group behavior, only one n equal to 2 is selected. So if you want to increase the number of possible theories, there is a possibility of adding an extra parameter to this Hodge Laplacian. And just by adding here a terms which depends on the curvature with an extra parameter lambda. This generalization reduces to the previous theory when lambda is equal to 1. So you can compute again the coefficients here of the beta functions, and you get exactly this formula for large values of n, and for c equal to 1. Again, you have C1, you have a different value, which is not obtained from this Cn plugin n equal to 1. So the situation improved a lot. Now we have much more theories which are asymptotically free in the ultraviolet. This is the blue region here in this picture. And you see the old theory is the red line. So the red points are the theories we had before, which were asymptotically free. Now we have a larger range of theories which are still asymptotically free. If we consider fixed n, for instance, n equal to 4, we have this range where the theory is asymptotically free. But if lambda is larger than that, the theory again is not asymptotically free. You can have a strongly interacting regime at very high energies, as you have in very low energies, the standard confinement theory. So in n equal to 3, the regime where you have asymptotic freedom is larger. But the special theory, n equal to 2, is always asymptotically free for any value of lambda larger than this 0.5 value over here. So it's the most favorable theory for have asymptotic freedom. But also in this plot, you remark that these boundaries of the regime where the theory stops to being asymptotically free are special points. These are the blue points where the beta function vanishes. So these theories at these particular points for n equal to 4, n equal to 3, n equal to 2 are finite theories. Do not require renormalization because you don't have asymptotically, you don't have UV divergences.
Manuel, sorry, 5 minutes left.
Okay, thank you very much. In these theories, none of these theories, which are finite, do have instantaneous solutions. In particular, if you compute the QCD potential induced by theta terms, you get different behaviors from the standard QCD, which might be useful for discussion of action physics. So now let's focus on the problems with ghost. So why this is not a real problem is the following. First of all, all these theories with lambda or without lambda, capital lambda or small lambda, in any case, the theory is BRST invariant. So which means that, as you have seen in the propagators, they are transverse. So there is no any problem with Faddeev-Popov ghosts and so on. In fact, they are not renormalized. And what is remarkable is all the high energy terms which were introduced as extra terms, apart from the Young-Mills term, do not require any renormalization because the radiative corrections to those terms are always fine. So only the Young-Mills term gets normalized, and this normalization is obtained by beta function of the gauge coupling G. But this implies, since these high derivative terms are not normalized, that the running of the extra dimension full parameter lambda, the scale, does not run. So it runs the opposite way with a different sign. Sorry, here there is 1 over n term in front of this beta G function missing. This implies that the effective mass of these ghost fields run to infinity for all theories which are not finite. So in finite theories, they do not run, but for all other theories, they run to infinity. So it means that you recover unitarity causality for free. So in those theories, the ghosts do not give rise to physical problems in unitarity and with unitarity and causality. So just to finish, let me just summarize the results. First of all, surprisingly, asymptotic freedom is not natural in high derivative theories. To have asymptotic freedom, you have to pay a price. So the price is that not to involve too many derivatives. You can only have at most 8 extra derivatives or 4 extra Laplacians in between the curvatures. If you include lambda, it's even worse. So the number of derivatives, if lambda is large enough, is reducing a lot, shrinking the domain of asymptotic freedom. And the extreme case is n equal to 2, where you have no constraints, but it's only one theory. Okay. The other output of this analysis is that the effective masses of extra gauss run to infinity, which is a good news because then you recover unitarity and causality. And what is missing is just the extension of this analysis to gravity, which is a work in progress. And what are the physical implications of these results? In particular, if something similar happens in gravity, as we have here, which restricts the number of extra derivatives you have. Thank you very much.
Manuel, is there any question, comment?
Yeah, one question, perhaps. Manuel, what happened with the anomaly in this case? The theory remain anomalous or not? You
have beta function. As long as you have beta function, you have.
If you come to fermions and
to fermions.
Yeah.
Yeah, that's a good point. So, you know, the coupling to fermions, if you do it in a standard, with a standard couplings, so no high derivative couplings, because you could also introduce. So, because of all this non-renormalization of higher derivative terms, you keep this in the ultraviolet. You don't have this in the deep ultraviolet. The graphs are finite.
Okay.
But if you, I'm meaning if there are two kinds of anomalies, the chiral anomaly, for instance, and the trace anomalies. Okay, trace anomalies, the beta function is exactly related to the one we have computed. With the chiral anomaly, since what is running in the loop are just fermions, you don't have gluons on the loop, so are not modified. So you get the same value of the anomaly.
Okay. Okay. Thanks.
Michael, please.
Hello, Manuel. Thank you for the interesting talk. My question is, from the point of view of the analysis of constraints of your theories, what is the difference between those cases of n, which are nice from your point of view with asymptotic freedom, and for higher values of n?
Well, this is a very good question and hard to answer because, naively speaking, these theories are very hard to analyze in the Hamiltonian formalism, you know. And this constraint analysis is, it has been done for very simple cases. But what I can say to your second question is that there is no difference between the asymptotically free case and the other cases. The problem is exactly the same. So it's a hard problem because it was analyzed by Ostrogradsky long ago, centuries ago. And these theories have some problems, which are called Ostrogradsky instabilities, which are the classical level, make the constraint analysis much harder than the standard one.
But in principle, you can introduce Lagrange multipliers and to rewrite your system without high derivatives in principle.
Yes, but involving more degrees of freedom.
Yeah,
you can do, yes. This has been done for simple models, for instance, in lower dimensions. But in 4 dimensions, which is the case we analyze, I don't remember some analysis of this full analysis till the very end of the constraint analysis. It's a hard problem.
Thank you.
Do you have time for more questions? I have a question, Manuel. you don't think that even if the theory is finite, you can renormalize it, because in some moment you need to fix the free parameters. So at least you will have to, I think, to have a renormalization scheme at which energy fix.
Yeah, but
in order
this
to,
is up to you. Yes, you are right. It's up to you. So it's like a mass in a theory which have no divergence on the mass. So lambda you have to fix. It's an external parameter you have to fix. Then the running of lambda is proportional to lambda times some logs which go and which make the effective lambda diverge. So, but of course you have to fix the scale where you subtract this. If instead of having dimensional regularization, we can introduce some mu scale, or there also too. So a mu scale you have to fix, but use this minimal subtraction. And we also add some finite term, which to some extent fix the scale. For instance, we introduce lambda QCD. And so this is a parameter. So we could modify this lambda QCD too. So you have, at least you have 4 parameters. One is the number of derivatives. The other one is this capital lambda. The other one is small lambda. And the other one is this control of the infrared, I mean, not infrared, intermediate regime, which is lambda QCD. So you have all these parameters to play with.
okay. Thank you very much.